Hey guys, welcome to another video in Machine Learning Made Easy, and in this video we'll be implementing the expectation maximization and our K-means algorithm using scikit-learn in Python. So scikit-learn is a great machine learning library that's written in Python. So we'll be implementing both the algorithms, and we'll be going ahead and observing the difference in performance between both the algorithms. I mean, when I say performance, it's going to be the accuracy score, and we'll also observe if we can conclude which algorithm performs better than the other given a specific data set. So yeah, we'll just start off with writing code. So we'll just as usual import our dependencies first. So we can say matplotlib.pyplot as PLT, and let's say sklearn.cluster cluster import KMeans, and we also need the data sets that come right out of the box and with scikit-learn. So we need scikit-learn. From scikit-learn we need import data sets, right? So these data sets come right out of the box with scikit-learn, so you can just import them and start working with them. So we need pandas and numpy as usual. Import pandas as PD and import numpy as NP. And in order to calculate or get the accuracy score, we need the accuracy score class from the metrics package. Learn.metrics. We need to import accuracy score, right? So our import dependencies are in place, and we'll just start to get data into our program. So we can. So for this implementation, we'll be using the iris dataset. So we'll be saying iris equals datasets dot load iris. So load iris is the method that's going to load the iris dataset into our variable. So yeah, that's there. So this is going to return a dictionary that's going to contain the target and the data and the target values. So we'll just grab our input values into X. So we'll construct a new data frame and say iris.data. So where the value for the key data in this dictionary is going to be the data frame for X, right? And we'll just print out X to just to see how our data looks like. So we'll just run this. So this is our data. So we have 150 rows in total, and we have 4 columns, and this is just the serial number that's assigned by pandas automatically, right? We have 4 columns, 0, 1, 2, and 3. So right now our column names are just integer values. So we'll just assign more legible column names to our data. So we can do that by using the columns attribute off of our data frame. So we can just pass in a list of strings that act as our column names for our data. Right? The first column is going to be the sepal length, and the second column is going to be the sepal width. The third column is going to be the petal width or petal length, and the last column is going to be the petal width. Right? Yeah. So that's how we assign columns. So we'll just take a look at our data set one more time. So after we assign the column names, this is what it looks like. So we have the column names, and now we can go ahead and grab our output data or the target values. So we can construct a new pandas data frame. We can pass in the target values from the iris dataset. So of course iris, again, the Y data frame also will not have the column names at first, so we can just run it and see. The column name is just 1, so we'll just quickly assign the column names, and I'll tell you what's going on. So we'll just pass in 1 value, so it's going to be targets, right? So then if we print out Y, so these are targets. It's just the serial number assigned by pandas, and we have target values as 0s, as 2s, and there are 1s in the middle of this data set. So I mean, it's just printing out some 20 to 30 the values, entries from the starting, and from the ending is just printing out the last 30 entries. So because there are a lot of values in between. So there are three kind of targets: the 0 target, the 2 target, and there's 1 target in between. So 0 represents one kind of category, and 1 represents another kind of category, and 2 represents the third kind of category. So there are basically 3 kinds of categories for flowers in this data set, at least in this target's value, right? So yeah, we have our input and output in place. So just get rid of that and clear the output. So once we do that, we can go ahead and build our model. So we can say build the KMeans model, and we can use our KMeans class to build an object and fit the model. So we can say KMeans equals KMeans, and we pass in the number of clusters. So number of clusters equals 3. So number of clusters here, this number basically denotes the number of categories that we want to classify our data into. So if you have number of cluster, that's n underscore clusters equals 3, it'll basically classify the given data set into 3 classes or 3 categories, right? So that's what n clusters specify. So then we have the clusters. So we can grab clusters by fitting and then predicting over this model. So we can say KMeans dot fit predict. So fit predict is a method which first fits the input data and then predicts it, right? So here the whole KMeans thing, the algorithm thing happens. So we can say we can pass in the input data frame, right? So we can quickly take a look at how our clusters array look. So it's just an array of values containing the categories, right? 0, as I said, 0 is one category of flowers, 1 is another category, and 2s are the third set of flowers. So it's just gives you back a cluster, which is an array of values that has this category names or target values, right? So once that is done, this is for the whole data set, right? So because since we have 150 entries, so there are 150 values in this array. So it just classifies each and every data point into a given target, right? So that's done. So now we're going to make our labels array. So we also need another dependency here, so which is this scipy.stats. So we can say from scipy.stats import mode. So scipy is another great library. So under the stats package you import mode. So mode is nothing but if you call mode and pass in an array of values, it's just going to give you the modal value of that array. So modal value, by modal value the value that's repeated most number of times, or the most common occurring value, right, in that array. So it's going to basically return a tuple, so of 2 arrays. One array is going to be the most commonly repeated value in every row of that array, and the second array is going to be the number of occurrences. It's going to represent basically the frequency of repetitions for each and every value in the first array, right? So I hope you get that. So if not, you just go ahead and read the documentation for mode under scipy. So it will give you a clear description of what mode does. So it's basically returning the modal value. So if you know statistics, if you're from a statistical background, then you know what mode, median, and mean, those stuff is. And then mode is nothing but the most commonly repeated value in an array or in a set of values, so as to say, right? So then we can just initialize an empty labels array. So we can say np dot zeros like and pass in our clusters array, right? So zeros like method takes in one parameter, which is an array of values, and it just looks at the dimensions of the of this array, which is passed in as an input, and then initializes a zeros matrix or zeros array to this variable. So it's just a way of saying give me an array of values with zeros like this one, right? So that's what we're doing by saying zeros like. So yeah, that's done. And now we're going to assign labels for each and every predictions that we have. So basically, we can run a for loop for every category that we have. We can say I in range 3, because we have 3 categories, and we can say category equals clusters equals I. So what we're doing right here is we are comparing wherever in the clusters array, wherever I is for example, at first I is going to be 0. So wherever I is going to be 0, it's going to return an array of Boolean values with true or falses, right? So for the first set of values, wherever the value is I, so in this case, in the first iteration, it's going to be 0. If the value of I is 0, and wherever there's 0 in the clusters array, it's going to be true, and all other positions is going to be false. So it's going to return that Boolean array into cat variable category. Then we can say labels of category. So wherever it's true, we are going to assign the mode value of iris.target of cat. Target of cat, right? And then we're going to grab the first. So as I told you, if you in the target, wherever it's true. So cat is basically representing an array of Boolean values. So wherever it's true in cat array, so just grab those values and find the mode of those values, right? So it's going to return at first, if I is 0, it's going to return 0. And we're just taking the first element off of this because mode method is going to return a tuple of 2 arrays. We're just interested in the first array, right? And that array is going to be assigned to the labels of cat. Wherever there are 0s in the first case, and in the second iteration it's going to be wherever there are 1s, and wherever there are 2s in the third iteration, and so on. So that's what we are doing by assigning the mode value to the labels of cat. So then we can calculate our accuracy score coming out of the for loop. We can say accuracy ACC equals accuracy score of we can pass in our target values first, target values, and then the labels that we got. So it just basically compares how accurately the predictions have been done for the given data, and then we can just print our accuracy score. Accuracy equals ACC, right? So we'll just run this quickly and see. So right now we've got an accuracy of 0.89, which is 90% of the data has been classified accurately. So that's a pretty neat job. So we'll see how the EM thing does. The EM algorithm works on this given data set, on the iris data set. So we'll just quickly plot stuff onto our canvas so that we can visualize how data have been classified, or how the clusters have been categorized. So for that we can say plt.figure, and we can just define our figure size. It's just going to take a tuple of values, so it's a 10 into 10 figure size, right? And we can also define our color map, just to make sure that we assign different colors to our clusters. So it can be a NumPy array, and we can define different colors inside this array. So one can be red, and we can have line. I like line color. So, and another can be blue, green, or black, whatever you want, whatever your favorite colors are. You can just define it here. So we just have our color map in place, and so now we'll just plot the actual classifications, right? So first we'll plot the real clusters, and then we'll plot the clusters that were categorized by the K-means algorithm. Then we'll perform the same classification using the EM algorithm, and then plot another graph showing the clusters that were categorized by the EM algorithm. Then we'll compare the accuracies of both the algorithm, and we can also visually take a look at how the classification of both the algorithms have are different, right? So we can plot the original classifications at first, classifications using petal features, right? We'll make use of the features petal. It's just going to be petal length and petal width, right? So we can say plt.subplot. So subplot basically takes three values. So it's just going to take the number of rows and the number of columns and the index where you want this plot to be. So I know I'm going to be plotting 3 different subplots, so I need a 2 into 2 number of positions of canvases or whatever it is. So it's basically giving me 2 rows and 2 columns to plot different subplots. And the first index, this is going to be the first index that I want to plot my original classifications in. And we'll just quickly plot a scatter plot. We'll just call plt.scatter, and we'll pass in the petal length and our petal width. And we'll pass in our color map as color map of targets, y.targets. So wherever there's 0, it's going to take red color. If the target is 1, it's going to take lines, blue for the value 2. And just quickly pass in s equals 40. So I'll just tell you in a moment what this s denotes, right? So we have generated a scatter plot. We'll just give it a title real quick. The title can be the real clusters. So this is the original clusters based on the target values that we already have from our data set, right? So the title can be real clusters. So it's always a good habit to have the x and y axis labels. The x label is petal length, or we just don't need underscores for this. So we can also assign a y label. I don't know why I'm unable to type today. Yeah, so that is done. So we already have the classifications of the K-means model, so we'll just quickly plot that out as well. So plot K-means model classifications. Oh my god, I always get that wrong, don't I? Yeah, classifications. So plt.subplot will define another subplot with the same amount of rows, same number of columns, and this time the index is going to be 2. The second index, the second canvas, the second subplot should be this one that we are going to define now. So we can have a scatter plot of passing same values, petal length and petal width. C equals color map of, this time it's going to be the labels. I'm sorry, I spelled it. Yeah, labels, right? This is going to be 40. Alright, so we'll just quickly, or instead of typing stuff too much, we'll just quickly do this. Right, so we have our X label, but these are K-means clusters. K-means clusters, right? It's again same thing, petal length and petal width. So now we can build a model off of our EM algorithm. So that's basically for a Gaussian mixture model, right? So we can do that by, or we'll go to another cell. Yeah, I mean this code is not clean, not so clean as our previous code. From our previous videos, from locally weighted regression and backpropagation. That's okay, but this is anyway, looks neat. Alright, so we'll quickly build the EM model. So it's general expectation maximization for Gaussian mixture models. So we'll just shorten it out by saying GMM, Gaussian mixture models. So for this, we need another dependency. Under scikit-learn, you need a package called pre-processing. Right? So before we actually work with data for Gaussian mixture models, we need to transform them into a distribution that has the mean value 0 and the standard deviation for this distribution has to be 1, right? So we need to transform the data in such a way that the mean is going to be 0 and the standard deviation is going to be 1. Okay, let's see how to do that. So we'll say transform data such that the distribution mean equals 0 and standard deviation equals 1. Okay, so in order to do that, we need this pre-processing package, right? So we can say scalar. We need to scale the data using pre-processing dot standard scalar, and we can call fit off of the scalar. We can pass in the input data. So right, and we can say the scaled x equals scalar dot transform, and then pass in the x. So this is going to transform the data into that distribution that we were talking about, so that the mean is 0 and standard deviation is 1. So we can finally get our x scaled, or just lowercase xs equals a new data frame, and that's going to take up the scaled x, and our columns will be our x dot columns, because since there's no change in that, it's a normal data set. And then we need to build our actual Gaussian mixture model. So for that, we need to import from sklearn.mixture, import Gaussian mixture, right? So we imported a Gaussian mixture, we'll just build the model off of it. So gmm equals Gaussian, it's not Gaussian, it's Gaussian mixture, and we'll pass in the number of components. So number of components in our case is going to be 3, right? So we'll just quickly grab the y values. We can say gmm underscore y equals, we can call the fit predict method off of our input data and just pass in our input data. Our input data in this case is the scaled x. The scaled x is xs, right? And we can, as usual, create a empty labels array. We can say zeros like. We can pass in our clusters, because the clusters remain the same. I mean, the shape of the clusters remain the same. And we can call the same for loop. The for loop is the same, so it's going to go from 0 to 3, or 0 to 2 technically, right? And then we grab categories equals the same way. We're going to say wherever gmm underscore y is equal to I for each and every case, or for each and every iteration, when it's 0, when it's 1, and when it's 2. So it's going to return an array of Boolean values into cat. Just, it's not cat, it's categories, right? It's just short for categories, it's cat. So then we are going to do the same thing here for labels of cat. Will be the mode value of iris dot target of cat, and then we're just interested in the first value, which is the mode value actually. All right, so this is done, and we'll just quickly calculate the accuracy for this model, accuracy score of our iris target, and our new labels. So labels will have the new values now. After, since we've used the same variable, it's going to be overwritten, right? And then we can quickly print out our accuracy again. Accuracy using gmm equals print out ACC here. Right. So we now have the accuracy. Before trying to print this out, we'll also plot our the subplot for visualizing the clusters of the GMM subplot. I can say subplot and pass in 2, 2, but this time the index is going to be 3 because it's going to be the third canvas inside our figure, right? So we can quickly do a scatter plot, pass in the petal length and our petal width, and then color map as usual. And color map, we can say GMMY this time because we're plotting for the labels of GMM. And S equals 40. I'll just come back to what this S is in a moment. So we'll just quickly assign a title. So GMM clusters, right? And our X label is going to be petal length, and our Y label is going to be petal width. Yeah, that is there. So yeah, I think we are all set to build both the models and run and classify this data into clusters. So basically 3 clusters to be precise. So we'll just quickly run this thing, and we got to right here, and if we run the last one we will get another one here. So I think it's better if we put the whole thing in a single cell, and so that we get the visualization in line, right? So okay, I just forgot to add this matplotlib inline. So this is just going to help you print your canvas in line into the Jupyter notebook. So you can call run all, right? So here, if you take a look at the accuracy, it's 0.893334 for the K-means model, because that's the model that we are building first, right? Here, K-means model, the accuracy is 0.893. Surprisingly, the Gaussian mixture model has an accuracy of 0.966, which is almost 100%. So it's 97% accurate. So I don't know what this is. We never printed any such thing anywhere. I don't know what this is. What is this? Output text of something. I don't know what it is. Let's not care about that. But here we have 3 canvases. It's quite cluttery, so we'll just say so here I can say plt dot subplots adjust, and we can pass in the height space. The height spacing can be something like 0.4. So then if we run it, so we'll just have that neat spacing between. We'll also have width spacing. Let's quickly see. Yeah, it's pretty sure it's W space 0.4 again. So yeah, now we have a neat visualization of our data. So these are the real clusters. So we have 3 set of classifications. So as to say, 3 kinds of flowers to be, for this data set. And so you can actually see clearly because of the color map that we applied. It's red, green, and blue. So it looks pretty neat. And after using the K-means model to classify or cluster this data, so we have the first category is pretty neat. It's 100% accurate. And here, if you take a look at some points over here, then you can see that some points which are supposed to be in the blue class have been classified as green. Right? So there's some inaccurate predictions right there. So that's why we have this accuracy score close to 90%. So if you take a look at the GMM clusters, so I think it's pretty close to what we can see here in the real clusters. This one's good. The red looks good, and there are only a couple of dots missing from the green. So other than that, it's quite similar, almost similar to the real clusters thing. So that's why we have our accuracy as 96.66%. So right, and so we can say, yeah, from this observation, So we used the same data set to build a model using K-means and the GMM, Gaussian mixture model, and then we used it to classify our given data point into 3 different clusters. So from accuracy score and also from this from these visualization stuff, we can conclude that the Gaussian mixture model, which uses the EM algorithm, right, the expectation maximization algorithm. So the clustering, which was based off of the EM algorithm, is more likely to match the real clusters, right? So as to say, I mean, you can just decide it just by looking at the accuracy score. So yeah, we implemented both the algorithms, and the visualization is pretty beautiful. And that's it for this video. So if you have any doubts or any queries, just leave it in the comment section below, and I'll put the links for this GitHub repository in the description of this video. Make sure to check it out. And yeah, I'll see you guys in the next video. Till then, take care, bye-bye, and please don't forget to subscribe to our channel. We'll come up with more machine learning content, and hit the notifications icon for regular updates. See you guys in the next video. Till then, take care, bye-bye.